July 15, 1942. Lieutenant Harry Smith is flying a P-38 Lightning over the Greenland ice sheet. His fuel is critically low. The weather has closed in, sealing the route to Iceland and blocking the turn back to their last Greenland base. Fuel is critically low, options collapse to zero. He has 0 options left. He initiates a forced landing procedure on the ice. In a catastrophic crash, kinetic energy tears airframes apart. But this is not a crash, it is a controlled ditching onto a surface that is both solid and yielding. Seconds before the aluminum belly touches the snow, Lieutenant Smith makes a technical decision that will resonate 50 years later. He cuts the mixtures and feathers both propellers. Feathering rotates the blades toward a low drag angle and can arrest windmilling fast. If a prop is still turning when it strikes snow, the impact can transmit destructive loads through the gearbox and mounts, so he kills the rotation before contact. By stopping them, Smith converts the violent energy of rotating steel into a static slide. The 12-foot propellers act as skids. The P-38 settles onto the ice. It slides, it stops. The structure is stressed but intact. Smith opens the canopy. He throws the keys to the aircraft onto the cockpit floor. He climbs out to join the crews of the 5 other P-38s and 2 B-17 bombers trapped with him. They are rescued days later. They leave the aircraft sitting on the surface, confident they can return to fly them out before winter. They are wrong. They have just crossed an irreversible threshold. They did not land on a runway. They landed on a geological conveyor belt. The primary objective of the Glacier Girl project, launched 50 years later, was to reverse this event. The goal was to locate the specific airframe flown by Smith, extract it from the ice, and restore it to flight status. But between the pilot leaving the cockpit and the recovery team arriving, the environment altered the evidence in 2 fundamental ways. First, the location changed. The Greenland ice sheet is not static land. It is a slow-moving fluid. The ice flows from the center of the cap toward the ocean. The P-38 did not stay at its landing coordinates. It drifted. Second, the depth changed. The team that returned in 1942 found the plains covered in snow. They abandoned the recovery. Over the following years, multiple expeditions attempted to reacquire the site and failed because they underestimated the vertical scale of the problem. Early estimates suggested the plains might be buried under 40 or 50 feet of snow. This assumption was a calculation error. It failed to account for the specific accumulation rate of this region of Greenland. The snow does not just pile up, it compresses. The weight of new snowfall presses the layers beneath it into a dense material called firn, and eventually into solid glacial ice. This process seals the object in a dark, high-pressure environment. By the time the site was reacquired with a high-pressure steam probe, the aircraft lay under roughly 264 feet of solid ice, on the order of a 25-story building. This number, 268 feet, is the defining constraint of the entire operation. It is the height of a 25-story building. It is a depth usually associated with submarine operations, not aviation archaeology. The failure of the first 12 expeditions was a failure of sensor logic. They were scanning for metal at a shallow depth. Their magnetometers and ground-penetrating radar systems were calibrated for a target that no longer existed in that horizon. The signal from the aluminum and steel was masked by the sheer mass of the ice overburden. The recovery team had to solve a blind geometry problem. They were looking for a specific needle in a haystack, but the haystack was moving and the needle was sinking deeper every year. The stakes were absolute. If they missed the target by 10 feet, they would drill a shaft into empty ice. If they hit the target directly with a mechanical drill, they would destroy the artifact they came to save. The aircraft itself, the P-38 Lightning, presents a unique recovery challenge. It is not a simple tube like the B-17. It has a twin boom design. The central pod contains the cockpit and guns. The 2 long booms house the engines and turbochargers connected by a horizontal stabilizer. This geometry creates a wide, awkward footprint. It is structurally complex. Lifting it requires controlling the load paths across 3 separate fuselage sections. If you pull too hard on the center pod without supporting the engines, the wing spar can snap. But the prize was worth the risk. Because of Smith's decision to feather the props and the cushioning effect of the snow during the landing, the aircraft was not a wreck. It was a time capsule. The keys were still on the floor. The logbooks were in the seat. The hydraulic fluid was still in the lines. The challenge was no longer about whether the plane survived the landing. The challenge was whether the plane could survive the recovery. The team faced a vertical wall of ice 268 feet thick. They had to go down, disassemble a 7-ton fighter plane by hand, and bring it back up a shaft barely wider than a man's shoulders. The ice does not negotiate, it only accumulates. To retrieve the machine, the engineers would have to stop fighting the cold and start using thermal dynamics to their advantage. They had to turn the ice against itself. The recovery of Glacier Girl is fundamentally an exercise in resisting static load. To understand the condition of the aircraft at the bottom of the shaft, one must understand the difference between snow and ice. When the Squadron landed in 1942, the surface was soft powder. It cushioned the impact, absorbing the kinetic energy of the slide. But as the decades passed, the environment shifted from a protective cushion to a crushing weight. The accumulation rate in this sector of the Greenland ice sheet averages roughly 5.5 feet per year. This sounds manageable in isolation, but over 50 years, it creates an overburden of massive proportions. The snow at the surface remains porous. As it gets buried, the weight of the new layers forces the air out of the crystal structure. The snow transitions into firn, a granular intermediate stage. At a depth of approximately 100 feet, the pressure becomes so intense that the firn fuses into solid glacial ice. By the time the recovery team arrived in 1992, the P-38 was sitting under 268 feet of this material. The physics of the wreckage site had changed. The airframe was no longer resting on the ground. It was suspended inside a solid block. At that depth, the airframe lives under overburden pressure and long-term ice creep, load that acts from every side and never stops. In deep ocean salvage, water exerts pressure equally in all directions. Glacial ice acts similarly over long timescales. It flows and pushes against every square inch of the submerged object. The pressure at that depth is immense, sufficient to deform aluminum and shatter plexiglass. The team found the first evidence of this destructive power when they located Big Stoop, one of the B-17 bombers that landed with the P-38s. The B-17 is a large aircraft with a cavernous fuselage. It is designed to hold a crew of 10 and thousands of pounds of bombs. Structurally, it is a large, hollow tube. When the ice pressed in, the B-17 could not resist the load. The fuselage collapsed. The wings remained, but the body of the bomber was flattened, reducing the once massive aircraft to a two-dimensional footprint. It was structurally unrecoverable. The P-38 Lightning offered a different structural profile. It is a fighter, not a bomber. Its design is compact and dense. The cockpit is a small pod, not a long tube. The twin booms are packed tightly with turbochargers, radiators, and landing gear mechanisms. There is less empty space for the ice to collapse. This high structural density meant the P-38 had a fighting chance against the hydrostatic pressure. However, the ice found the weak points. The plexiglass canopy, designed to hold back air pressure at altitude, stood no chance against the weight of the glacier. It was crushed, filling the cockpit with ice. The air scoops and intakes, made of thin aluminum to channel wind, were flattened against the engine cowlings. The weight pressed the airframe down, distorting the round sections into ovals. But crucially, the main spars of the wings and the heavy steel of the engines held their shape. The plane was compressed, but it was not destroyed. While the physics of the ice threatened the structure, the chemistry of the ice worked to save it. This is the preservation paradox of the site. In a marine environment, a saltwater wreck at this depth would be consumed by corrosion. Chlorides would eat the aluminum. Galvanic reaction would weld dissimilar metals together. In the jungle, humidity and biological growth would rot the rubber and fabric components within years. The glacier offers a sterile, anaerobic environment. Encased in ice, the aircraft was cut off from oxygen. The temperature remained constantly below freezing. This halted the chemical processes of decay. There was no rust on the steel control cables. The aluminum skin did not oxidize. The rubber tires and hydraulic hoses did not rot. They simply froze. When the team drilled down to inspect the aircraft, they found a machine that looked confusingly new. The paint was vibrant. The stencils were legible. The metal shone under the light of the probe. It created a stark contrast, a structure that was physically battered by pressure but chemically pristine. This dictated the recovery strategy. The team was not dealing with a pile of scrap metal. They were dealing with a restoration-grade artifact that had been stored in a violent freezer. If they could relieve the pressure without damaging the skin, the aircraft could be returned to flight. But finding the aircraft was only the first variable. The ice sheet had added a vector of movement that complicated the recovery geometry. The location where Lieutenant Smith landed was not the location where the plane now rested. The entire column of ice, 268 feet deep and miles wide, was sliding toward the coast. The search team had to account for this drift. They were not just drilling for a static object, they were intercepting a slow-moving target. The coordinates had to be calculated by modeling the flow of the glacier over half a century. A vertical shaft drilled today might miss the plane tomorrow if the drift rate was miscalculated. The environment had effectively hidden the squadron twice, once by burying it under a 25-story building of ice, and again by moving it over a mile from its origin. The recovery would require a method that could penetrate the depth, manage the pressure, and hit the drifting target with surgical precision. The coordinate system used in 1942 failed the moment the calendar turned. When Lieutenant Smith and his squadron abandoned their aircraft, they recorded their position on a map. In aviation, a coordinate is usually a fixed point on the surface of the Earth. But on the Greenland ice cap, the surface is not fixed. It is a slow-moving river of solid ice flowing from the high interior toward the coast. For 50 years, the Lost Squadron did not stay put. The entire geological shelf containing the aircraft drifted. By the time the search teams reacquired the site decades later, the shifting ice had carried the airplanes about 2 miles from the original landing coordinates. This movement created a complex geometry problem for the search teams. To find the wreckage, they could not simply go to the historical latitude and longitude. They had to calculate the drift vector. This meant modeling the speed of the glacier, the terrain beneath the ice, and the direction of the flow over 5 decades. If the calculation was off by a fraction of a degree, the search box would be hundreds of yards away from the target. This drift explains why 12 previous expeditions failed. Some teams looked at the original coordinates. Others accounted for the drift but underestimated the depth. They were walking directly over the aircraft, but their sensors could not penetrate the massive overburden of ice. The breakthrough for the 13th expedition came from a combination of refined drift modeling and deep penetration sensor technology. The team utilized high-power ground, penetrating radar, and proton magnetometers. These instruments do not see a picture of a plane, they see anomalies in the magnetic field and the density of the subsurface material. The challenge was distinguishing the targets. The ice field contained 2 B-17 bombers and 6 P-38s. The magnetometers picked up the large magnetic signature of the B-17 steel components first. The Big Stoop bomber became the reference point. Once the team located the bomber, they could map the relative positions of the fighters. The P-38s were smaller, denser targets, arranged in a specific formation relative to the larger planes. But a sensor return is not proof of identity. It is just a ghost on a screen. The team needed physical contact to verify the depth and the specific identity of the aircraft. They needed to confirm they were targeting a P-38 and not a B-17, as the extraction method for the smaller fighter would be radically different. To achieve this without digging a massive shaft, they used a thermal probe. This was a steam-heated nozzle attached to a long hose. It melted a narrow, inch-wide hole down through the ice. It was a surgical strike. The team lowered the probe, feeding out line, watching the depth counter tick past 200 feet. At 268 feet, the probe stopped. It had hit a hard object. When they pulled the probe tip up, they found traces of hydraulic fluid and paint. They had physical contact. This moment highlighted the surreal nature of the site. Brad McManus, the pilot of one of the other P-38s in the squadron, visited the expedition site during the search. He stood on the ice surface, looking at a white, flat horizon. In his memory, he had left his plane on the surface. But in physical reality, his aircraft was now a mile away horizontally and buried under the equivalent of a 25-story building vertically. The discrepancy between his memory and the sensor data was the tangible measurement of 50 years of glacial movement. The probe data confirmed the depth at 268 feet. This number was critical. It was deeper than anyone had feared. At this depth, the pressure is approximately 8 atmospheres. But more importantly, the depth dictated the structural limits of the access shaft. If they dug a wide hole, the walls would be unstable. If they dug a narrow hole, the equipment might not fit. The probe proved the aircraft was there, but it also proved that the ice was deep enough to exhibit plastic flow. A shaft drilled at this depth would not stay open indefinitely. The pressure of the surrounding glacier would try to squeeze the hole shut like a self-healing wound. The team now had positive identification and a verified depth. They had a target lock, but they also had a severe constraint. They could not use standard excavation equipment. Bulldozers could not move 200 feet of ice. Mechanical augers would bind and snap in the shifting shaft. The solution required abandoning mechanical force entirely. To reach the P-38, they would have to stop thinking like miners and start thinking like plumbers. They would not dig the ice out. They would melt it. The engineering team faced a constraint that ruled out almost every standard tool in the excavation handbook. They needed to move 3,000 tons of ice to reach the aircraft. In a normal mining operation, this would involve blasting, drilling, and hauling spoil to the surface. But this was not rock. It was a plastic medium that shifted under pressure. A mechanical auger operating at 200 feet would bind, torque, and snap as the ice moved. Furthermore, the vibration of heavy drilling risked collapsing the fragile aluminum structure waiting at the bottom. The decision was made to abandon mechanical cutting in favor of thermal mining. If you cannot cut the ice, you must change its state from solid to liquid and pump it away. The tool engineered for this task was a custom device nicknamed the Super Gopher. It was not a drill, it was a thermal descent vehicle. Physically, it resembled the nose cone of a missile, roughly 4 feet in diameter. The cone was wrapped in heavy copper coils. Hot water, heated by surface generators to nearly 200 degrees Fahrenheit, circulated through these coils. The operation was a slow, gravity-fed descent. The team lowered the Gopher onto the ice. The heat transferred into the surface, melting a perfect circle. As the ice turned to water, the Gopher sank. The rate of descent was agonizingly consistent, approximately 2 feet per hour. This was not a fast process. It was a test of patience governed by the specific heat capacity of water and the latent heat of fusion of the ice. A critical subsystem was the liquid management. As the Gopher melted its way down, it generated hundreds of gallons of water. If this water remained in the shaft, it would lose heat to the surrounding glacier and refreeze, sealing the Gopher inside a tomb of its own making. To prevent this, a complex array of sump pumps moved the meltwater up the hose lines to the surface. The thermal mining process was a closed loop. Heat goes down, water comes up, and the shaft stays open. Day after day, the Gopher descended. At 2 feet per hour, the journey to the aircraft took over 5 days of continuous melting. The walls of the resulting shaft were smooth and glass-like, polished by the descending heat. This smoothness was vital. Later, delicate aircraft sections would have to slide up this tube without snagging. When the Gopher finally broke through to the level of the aircraft, the strategy shifted from vertical penetration to horizontal expansion. A 4-foot hole gives you access, but it does not give you a workspace. The team had to carve a hangar inside the glacier. They lowered steam hoses down the shaft. By directing jets of high-pressure steam laterally, they melted a cavern around the P-38. This room eventually grew to be roughly 50 feet wide. The environment inside this ice cave was surreal and hostile. It was not the silent, dry freeze of the surface. Because of the steam hoses and the melting ceiling, it was essentially a cold, dark rainstorm. The temperature hovered just above freezing. Water dripped constantly from the roof. The team worked in heavy rain gear inside a glacier. This constant moisture presented a new hazard. The P-38 had survived 50 years because it was frozen and dry. Now, the recovery team was introducing heat and humidity. The risk of flash corrosion on the steel engine parts skyrocketed. The environment that allowed them to work was simultaneously attacking the artifact. The physical interaction with the aircraft began under these wet, dark conditions. The first view of the plane confirmed the sensor data. The weight of the ice had done its work. The canopy was shattered. The cockpit was filled with solid ice. The heavy engines were sagging on their mounts. However, the thermal mining approach proved its worth. The Gopher had not touched the plane. It had stopped precisely above it. There were no pickaxe marks, no shovel scrapes, and no vibration damage. The aircraft sat in the center of the carved cavern, heavy and gray, released from the pressure but still trapped 268 feet below the surface. The team now faced the geometry problem of extraction. The shaft was 4 feet wide. The P-38 wingspan was 52 feet. The center section was 17 feet wide. The aircraft could not come up in one piece. The engineers had to disassemble the plane in situ. This meant taking apart a complex machine in a dark, dripping cave using only hand tools. They had to remove the propellers, the engines, the outer wing panels, the tail booms, and the horizontal stabilizer. Every bolt they removed was a victory against the corrosion that would start the moment the parts hit the fresh air. But the disassembly had a hard limit. The center section, the pod containing the cockpit, the nose guns, and the inner wing roots, was a single structural unit. It could not be taken apart. It was 17 feet wide and weighed nearly 7,000 pounds. It was the heart of the aircraft, and it was far too big for the 4-foot exit door. The team had to enlarge the shaft or find a way to orient the massive component to fit the tube. They were about to attempt a lift that relied on rigging geometry and a manual hoist system so sensitive that a single mistake would send 3 tons of history plummeting back to the bottom. The recovery of the lost squadron ultimately coalesced into a single geometry problem. The team had successfully melted a vertical shaft 4 feet in diameter. However, the center section of the P-38, the fuselage pod comprising the cockpit, the radio compartment, and the inner wing roots, was 17 feet wide. The engineers faced a binary trade-off. They could cut the airframe into smaller pieces, destroying its structural integrity and its historical value, or they could find a way to fit a 17-foot wide object through a 4-foot wide tube. They chose the latter. The solution was not to widen the hole, which would have required melting thousands of tons of additional ice. Instead, they chose to disassemble the aircraft in situ and orient the massive center section vertically. This decision defined the technical pivot of the entire operation. It shifted the mission from a salvage job to a precision disassembly task performed under the most hostile conditions imaginable. In situ disassembly is a standard procedure in aviation maintenance, but it is typically performed in a heated hangar with overhead cranes and hydraulic jacks. The team in Greenland had none of these luxuries. They were working inside a dripping ice cave, standing on an uneven floor of slush illuminated by portable halogen work lights. The process began with the peripheral components. The mechanics had to unbolt the propellers, the 12-cylinder Allison engines, the twin tail booms, and the outer wing panels. Each component presented a snagging hazard. The ice had flowed around the aircraft, encasing parts of the structure. In some areas, the team had to use steam wands to surgically release the aluminum skin from the grip of the Glacier before a wrench could even be applied. The environment imposed a severe logistical tax on the workforce. The commute from the surface to the cavern took 25 minutes. Workers rode a makeshift elevator cage down the wet 4-foot shaft. Once at the bottom, they worked in shifts limited by the cold and the dampness. As the lighter components were hoisted to the surface one by one, the cavern emptied, leaving only the center section. This was the critical mass. Weighing approximately 7,000 pounds, it was the heaviest and most awkward component. It contained the main spar, the structural backbone of the aircraft. If this spar was bent or cracked during the lift, the aircraft would never fly again. The engineering challenge was rigging. You cannot simply tie a rope around a fighter plane and pull. The stress would crush the aluminum skin or warp the frame. The team designed a custom steel cradle, a lattice of beams that wrapped around the center section like an exoskeleton. This cradle distributed the lift loads into the hard points of the wing roots, bypassing the fragile skin. Once secured in the cradle, the center section was rotated 90 degrees. It hung nose down, a 17-foot wide airplane turned into a 4-foot wide cylinder. The lift system itself was a study in mechanical discipline. The team did not use high-speed electric winches. The risk of the load snagging on the ice walls was too high. If the 7,000-pound section caught a ridge of ice while moving at speed, the cable tension would spike, potentially snapping the line or collapsing the shaft walls. Instead, they used a manual chain hoist. The gear ratio was extreme. It required 4 full cranks of the handle to raise the load 1/4 of an inch. This was not a moment for speed, it was a moment for tactile feedback. The operators on the surface could feel the tension in the chain. If the load bound up, the resistance in the crank would tell them instantly, allowing them to stop and adjust before damage occurred. Inch by inch, the heart of the P-38 rose through the ice. It traveled past the layers of fern, past the transition zone where the snow turned to ice 50 years prior. It moved from the crushing pressure of the deep glacier toward the surface. The lift took hours. There was no sudden breakthrough, no dramatic surge. It was a slow, rhythmic conversion of human energy into vertical distance. Finally, the nose of the aircraft broke the surface of the melt pool. The condition of the metal confirmed the validity of the preservation paradox. The green anti-corrosion primer was intact. The aluminum was bright. The structure was heavy, cold, and wet, but it was whole. The decision to invest in the thermal shaft and the slow manual lift had paid off. The successful extraction of the center section marked the irreversible success of the recovery phase. The glacier had surrendered the machine. The team had achieved positive control of every structural component. They did not just have a collection of parts, they had a complete aircraft. But as the P-38 sat on the surface of the ice sheet, bathed in sunlight for the first time since 1942, a new clock started ticking. The ice had acted as a stabilizer. Now, exposed to oxygen and thermal cycling, the chemistry of the airframe began to change. The mission shifted instantly from extraction to stabilization. The recovery was over. The race to save the metal from the atmosphere had begun. The moment the P-38 broke the surface of the melt pool, the operational environment inverted. For 50 years, the primary threat to the airframe had been physical pressure. The ice had squeezed the fuselage, crushed the canopy, and bent the leading edges. But chemically, the aircraft was stable. It was locked in a cryostatic hold, protected from the oxidative decay that consumes aluminum in the open air. As the components sat on the Greenland ice sheet, awaiting transport, the clock restarted. Oxygen and moisture began to attack the steel alloy engine cylinders and the aluminum skin. The recovery team had to transition immediately from heavy lift engineers to preservationists. They washed the airframe with fresh water to remove any potential contaminants, although the glacial ice was remarkably pure. They applied corrosion inhibitors to the vulnerable steel surfaces. The aircraft was crated and shipped to a hangar in Middlesboro, Kentucky. Here, the project shifted from an excavation logic to a forensic restoration logic. The objective was not merely to display the aircraft as a static exhibit. The goal was to return it to airworthiness. This is a fundamentally different standard of engineering. A museum piece only needs to look like an airplane. A flying machine must handle aerodynamic loads, vibration, and thermal stress without catastrophic failure. The restoration team faced a critical question regarding the metal itself. This is the concept of fatigue life. Metal has a memory. Every time an aircraft wing flexes in flight, or every time a landing gear strut absorbs an impact, the crystalline structure of the metal accumulates microscopic stress fractures. Over time, these accumulate until the part fails. Glacier Girl had not flown many hours in 1942, but she had endured 50 years of static crushing loads. To certify the aircraft for flight, the engineers had to inspect every square inch of the structure. They used non-destructive testing methods, including X-rays and dye-penetrant inspections, to look for invisible cracks in the main spars. The results confirmed the unique nature of the recovery. The ice had deformed the skin, but it had not fatigued the core structure in the way that thousands of flight hours would have. The bones of the aircraft were young. The restoration process took 10 years. It was a slow, methodical reconstruction. The team disassembled the airframe down to the individual rivets. They straightened the bent bulkheads. They replaced the crushed air intakes, but they did not build a new plane. The defining statistic of the Glacier Girl project is the parts retention rate. In a typical warbird restoration recovered from a crash site or a scrapyard, the team might save 10 or 20% of the original material. The rest is new metal, fabricated to match the old patterns. Glacier Girl flew again using approximately 80% of her original parts. The wings, the fuselage, the tail booms, and even large sections of the wiring harnesses were the same components that Lieutenant Smith carried to Greenland in 1942. The engines provided the most striking validation of the ice preservation. The twin Allison 12-cylinder engines were filled with hydraulic fluid and oil before they were buried. When the restoration team opened them up 50 years later, they found the internals in factory-new condition. The crankshafts, the pistons, and the bearings showed zero corrosion. They were cleaned, inspected, reassembled, and mounted back onto the airframe. The heart of the machine was original. This high retention rate was only possible because of the decision made in the opening seconds of the event. If the pilot had landed gear down, the strut collapse would have twisted the spars. If he had not feathered the props, the engines would have torn themselves loose. The discipline of the 1942 landing enabled the fidelity of the 2002 restoration. On October 26, 2002, the loop was closed. Glacier Girl taxied onto a runway, ran up her 60-year-old engines to full power, and lifted off. The flight was not just a nostalgic event, it was a technical proof. It demonstrated that an aluminum semi-monocoque structure could survive a 50-year immersion in a flowing glacier, endure the crushing weight of a 25-story building, be disassembled in a freezing cave, and still retain the structural integrity required for high-performance flight. The aircraft is now capable of speeds exceeding 420 miles per hour. It flies at air shows, pulling G-forces that would fold a compromised structure. It does not fly as a replica. It flies as the original chassis, serial number 417630. The legacy of the project is not just the physical airplane, it is the validation of the survey and recovery methodology. The operation proved that deep ice recovery is possible without destroying the artifact. It proved that thermal mining can create a surgical access path through hundreds of feet of overburden. And it proved that with sufficient preservation discipline, the boundary between a lost wreck and a living machine is not permanent. The P-38 trapped in the ice was a static victim of the weather. The machine that flies today is a testament to the engineering required to reverse the consequences of the environment. The ice does not negotiate, but with enough heat, patience, and precision, it can be made to yield its prize.